Now, we'll continue now. You can look up, please. Yes, Lee. Mute.
Yeah, that's difficult.
No, I know it's difficult. Probability trees. Okay. Are we looking? Yeah. So, for these problems, we're looking at events where it's good to think about one event happening after another event. So, let's take an example here to explain what a probability tree is. So, we imagine, for example, in this one, the student has two ways to get to school. They can walk or they can take the bus. So, we'll start here. And then the student can either walk or they can take the bus. And in both cases, there's two outcomes from that. They'll either be on time or they'll be late. And in the second case, if you take the bus, they'll either be on time.
Not an argument.
Yeah, well, we'll reflect that with the probabilities, or late. So we'd imagine that this student takes the bus most mornings, so we'll say 0.7. This means there's a 70% chance that they'll take the bus in the morning.
So it's one student.
One student, yeah. And then here there's a 0.3, then there has to be a 30% chance that they walk, because the total still makes 1. Now, if they walk, we'll say there's a 0.9 chance they're on time, but a 0.1 chance that they're late. And if they take the bus, we'll say there's a 0.8 chance that they're on time, and a 0.2 chance that they're late. So the probability trees have the advantage of being able to consider different possibilities as you sort of travel through time. In the story here, we can have different probabilities for being late depending on what happened previously. So probability trees work really well when one event follows another event. This is the key. So now the question is, how do we use them? So the way probability trees work is you multiply across. So for example, if I said what is the probability that the person walks and is on time, that means we start here and we say they walk and they're on time, so that's 0.27. The probabilities multiply as you travel through the tree. So that's 0.3 times 0.9, which equals 0.27. So that's our first example. We'll have a look at more examples now. If you can write that down, that'd be great. We'll add in more now. Walks and is late. Walks, I mean to say, takes the bus and is on time. Takes the bus and is late. Okay, what's the next one? Walks and is late. 0.3 multiply 0.1, which equals 0.03. Takes the bus and is on time. What's that one? 0.7 times 0.8, please. 56. And then lastly, takes the bus and is late is 0.14. Now, I want you to notice here, these two add together to make 1. These two make 1. These two make 1. Walk and is on time, 0.27. Walks and late, 0.03. Takes the bus and is on time, 0.57. Takes the bus and is late, 0.14.
Adding up 1.
These should also add up to make 1 as well. Because at the end of the story, the student must be one of these. So it has to make 1. Yeah?
Yep.
Okay, let's look at this, but with some more difficult examples now. So these examples look at and. Can I scroll down? Yeah. Okay, now let's have a look at or. So, let's calculate probability that the student is late for school. So when we think about the student being late, there's two ways that that can happen. The first way is that they walk and are late. Yeah. Or they walk, thank you, bus and they're late. So there's two ways they could be late. They could walk and be late, or take the bus and be late. The way we deal with or in probability trees is we add. Walk and late, well, we worked that out earlier. What was walk and late? 0.03. And bus and late? 0.14. So this one here is 0.17. That's the probability that they'll be late. Now, if I said to you, what's the probability that they're on time? Well, probability of being on time is the same as the probability of not being late, obviously, which is the same as 1 minus the probability of being late.
Such a good student.
Yes. Which is 1 minus 0.17, which is 0.83. Okay, we can write this one down. Why 1 minus? Yeah, because the total needs to make 1. So, for example, imagine there was a 0.6 chance of being late, then that means 0.4 chance of not being late. 0.9 being late, then that means 0.1 not being late. Can I continue now with another example of this? One sec, yep. So we've looked at and, we've looked at or, we've looked at not. Last one to look at is the given that. So we have and, or, not, now given that. Can I scroll down now, Ian? Yep. Okay, so let's have a look at given that. So what is the probability that the person, the student, took the bus given that they were late? So this is a situation where you have a student in front of you, you know that they're late because they're late, and you want to know what was the probability that they took the bus. We feel like it should be pretty high because in the probability tree, you realize in the late scenario, in the bus situation, you're more likely to be late than in the walking situation. So if the student is late, which is more likely, that they took the bus or that they walked? Well, that they took the bus, because it's more likely to be late when you take the bus. So we want to calculate what exactly that is. So we could think about this again like a table. We have walk, bus, on time, and late. So when we did this in the last section, what did we put on the bottom here?
2.17.
No, what did we, tell me, describe what we put on the bottom here. What we put on the bottom in the last situation is total late. Yeah, total late. That's something I've already worked out. 0.17. What did we put on the top?
The bus.
The bus
0.03.
is late.
Yeah, bus and late. Yeah, so like here it was looking at the total for late, and you want to know the people who take the bus, but only from those who are late. So you're only looking at this one here, yeah. So this was bus and late. What was bus and late?
0.14.
0.14. So this is going to be a pretty big number, but we thought it would be because we felt that if the student's late, it is more likely that they took the bus. What is the number here?
14, 17.
No, I can see 14 and 17.
Oh,
Thank you.
We have to do
My eyes still function. What I want is the calculation here. 823. So there's an 82% chance that if the student is late, it meant that they took the bus. Again, you kind of expect it to be higher than 50% anyway. So this is a little bit messy to try and do it by a table. Let's see if we can work out a formula. If I scroll down a little bit here. So we're basically trying to get a formula for what is the probability of A given B. And if we think about the table, we can have, for example, A, not A, B, and not B. So here, what did we put on the bottom for this one? It was B, the total for B. So that would be like this number here for B, so that's B. And then what went on the top? If you think about it as a table, A and B, yeah. So actually, if you want, you can just think about this as a formula. The probability of A given B is probability of A and B over B. Once you write that down, we're going to do a very, very important example next. Okay, can I scroll down? Yes? Okay. So like I said, this next example is very important, and it has some important words in it too. So here, we are given a person a drug test to see if they are a drug user. So this drug test, we say is 99% not accurate, sensitive, and I'll explain what that means now. And then we also say that drug test is 99% specific. So if we say a drug test is 99% sensitive, that means that if the person is a drug user, 99% of the time it will say they're a drug user. So in other words, this is the probability that the test will say positive results, they're a drug user, given that they actually are using drugs. 99% specific, you could probably guess now what this means. What do you think? That's the probability the test says negative result, they're not a drug user, given that they actually are not a drug user. Not a drug user then. So it looks like this test is a pretty good test. if the person uses drugs, then 99% of the time it will give a positive result. If the person does not use drugs, 99% of the time it will give a negative result. We'll also say for this question, the probability a person uses drugs, we'll say it's quite small, 0.5% of the population, which is 0.005 then.
The sensitive and specific actually means the same thing, right? But it's a different sign.
They don't mean the same thing because these could be different numbers. For example, some tests are better at detecting drug use and giving a positive result than detecting non-drug use. I think in real life this number be much higher than this number, like this could be maybe 89%. It's easy to detect if someone's using drugs because it would show up in their blood, but to detect that they're not using drugs is more difficult because you're trying to show that something is not there, you know. Like, for example here, what's the probability that if there's students in this class, I see students in this class? Probably quite high, right? Because if you're in the classroom, I should see that you're in the classroom. But if I say, okay, what's the probability that I say there's no students in this class, if there's actually no students in this class, I can't be as confident because maybe a student is hiding under the table. It's a bit like with the drug use. If the person uses drugs, maybe it's easier to get a positive result than if they're not using drugs. It's harder to get a negative result. So in real life, this number will probably be less, like maybe 89%. But for this question, I'll say both are 99.
So,
Yeah.
what was that percentage?
Which one?
The 0.5?
That is how many people actually are drug users. For a probability that a person uses drugs is 0.5%.
So that's given in the question?
This is all given. Now we'll have a calculation now. Okay. Can I scroll down now to have the questions? So are we happy with these words sensitive and specific? No? What's confusing you, Fawn? You know what drugs are? Yes? So if a person uses drugs... No, not cool. If a person uses... Yeah?
But the drug mean in here, good drug or bad?
Bad drugs. Is it okay? Yeah.
The cold one.
Cocaine.
Yeah, cocaine. Yes. Yes. Why do you know words like this and not words, you know? Okay. So, Yusuf, there's 4 situations that could happen here. Good, Yusuf. Listen, please. Right. There's 4 situations that could happen here. The first one is the test is positive and the person uses drugs. The test is positive and the person doesn't use drugs. Obviously that's a bad situation. The person doesn't use drugs but they have a positive test.
How can it?
Because the test isn't 100%. It's not perfect. The next situation is the test is negative and the person actually doesn't use drugs. And then the next situation is the best for the person. They get a negative test result and they actually use drugs. So this is win-win for the person. They use drugs and they have a negative test result. Yes? So let's see what we want. I want to calculate what is the probability the person actually uses drugs given that the test is positive.
99%.
Now you see, it seems like it, but remember earlier we had an example where we saw A given B, we did not get the same number as B given A. Yeah, so actually it seems like at first it should be 99, but it turns out it's not. The person got a positive test result, so you know the test result is positive. This is like real life. A person takes a test result, you see it's positive, you know it's positive, and you want to know what's the probability that they use drugs. Yeah. Okay. Do you understand what we're calculating here? Probability they're a drug user, given that you know their test result is positive. You think it's 99. It won't be 99, but what do we think? Will it be high? Will it be low? What do you reckon? We would think it'd be high. If they have a positive test result, then we think it's likely they're a drug user. That's the idea. So let's calculate it. The formula I gave you.
Don't we need the probability of getting the positive result first?
Please be quiet and let me do it. Then you can ask me a question. I'm in the middle of doing it. I think I've given you all the information. We'll see. Okay. So probability drug user given that positive test result. So using the formula we had previously, that is probability of drugs and positive result over positive result. Yes? I know, I'm getting there. Now, let's see. I think I'd like to draw a probability tree just to help a little bit here.
To transform from a percentage to
oh yeah, this is 0.99 and this one here is 0.99. Okay. So let's just look at the bottom here. Positive test result. There's two ways the test result could be positive. Firstly, they could be drug users and get a positive result, or not drug users and then get a positive result. So on the bottom we have probability of a positive result given that they use drugs, or probability of a positive test result given that they don't use drugs. Yes?
what?
Yeah.
We saying that question drugs are used in saying the question drugs are given to.
Yeah, we know these numbers here. Yeah. So this one here is 0.99. Okay. Can I scroll down a bit? Drug using and positive result. Okay. Right. If we look here, which numbers do we know? I think we know this one. Do we know this one?
Yeah, it's 1 minus
0.99.
0.99. So the denominator is 1.
No, this is not 1 minus 0.99.
0.01.
No, not that one. Yeah. So this one here, I'll write it on the top here. Probability of drug use and positive result all over. Is it okay if I scroll a bit to the right for a moment just to get this in? Okay. So let's simplify each of these. Do you remember what you do for and in the probability tree? You multiply. So on the top is probability of drug use. Do we know this? We do. I give it to you. Probability of a positive result. Yes? And then down here, probability of positive given drug plus probability of positive given not a drug user. Okay. So on the top, let's fill it out. What's the probability that they use drugs? 0.005. Do we know the probability of a positive test result? No, we're trying to work that out. I feel like I did something wrong here. Let me think. One moment, please. I'm going to start this again.
Oh,
Don't complain.
no, I'm feeling.
Just morning.
Yes. Okay.
Morning.
I'm sorry. Let me start this again.
Morning master.
Be quiet or GTFO. Thank you.
It's a good song by J. Cole.
No. Be quiet. Thank you. I'm trying to concentrate. It's very difficult to concentrate with both a headache and you in front of me. Thank you. Right. So, I'll draw it as a probability tree just to make it a bit easier. So, at the very beginning, the person can either use drugs or not use drugs. How many people use drugs? 0.005. So, non-drug users? 0.995. Okay. And then drug users, you have two possibilities. You can get a positive test result or negative. Positive or negative. Okay. If they use drugs, what's the probability of a positive? 0.99. And of a negative? 0.01. And here? 0.1. Because this one was 0.99. Okay, that's a bit better, I think. Can you, as an example, all calculate for me probability that you get a positive result and probability that you get a negative result? So positive, to help you, is this one. You could have drug and positive or not drug and positive. Can everybody calculate this, please? Positive result? This one is 0.015. And you've done both this times this plus this times this. Okay. And then get a negative test result. That would be in blue here. You can get drug and negative and not drug and negative. So calculate that one, please.
So we add them or multiply them?
You multiply and then add. So for example, you do 0.005 times 0.01 plus 0.995 times 0.99. 0.98. 5. Yeah? 1. Yeah? Okay. Right, now let's calculate what we were trying to calculate a moment ago. It'll be much easier now that we have the probability tree. So we were looking for a probability that the person uses drugs, given that it's a positive test result. So we said that is drug and positive over positive. On the bottom we have 0.0150, and then on the top it will be 0.005 times what? 0.99. So this is what we were looking for. Let's see what we get.
0.33.
Yes. .33. Now just think about how surprising that result is. What you're saying is, if the person tests positive, what's the probability that they're a drug user?
0.33.
Not what you were expecting. You were expecting if someone has a positive test result, it should be likely that they're a drug user. This
So
better be good.
If I get tested for a drug, the probability of me getting a positive result is 0.67.
What do you want? You want to calculate the probability of getting a positive result.
But not a drug user.
Okay, what was this probability of a positive result and not a drug user? Let's calculate that. What do we have on the top?
No, the other way around. D dash given that's positive.
What's the probability that the person does not use drugs given that they have a positive result?
Yeah.
That's the probability that they don't use drugs multiplied by it's positive. So what was that, please? don't use drugs is...
Is it not 1 minus the answer
Hi-
above?
Let me do it, please. Faisal, please. Okay, not using drugs and positive over positive. Okay, not using drugs and positive. 0.005 times 0.99 over 0.0150. I'm sorry, on the top is 0. Let me just get my pen back. 0.995 times 0.01. Okay, what's that?
0.6.
Yeah, is 1 minus. So if the person tests positive, there's a 67% chance that they're actually not a drug user, even though they tested positive. Yeah. Let's have a look at the other one. What is the probability that the person does not use drugs, given that their test result was negative? Can you calculate that? Yeah. You want to know, they got a negative test result, what's the probability that they don't actually use drugs? So, can you calculate that, please? Did you get this one?
0.99.
0. Point. And this one, please?
0.9999.
For this one?
No.
Oh, the previous one? 0.
999.
Really?
No.
4 minutes. 4 minutes.
You mistyped. Okay, 0.999. Okay. Yeah. Next one, please. Drug user, given that they have a negative test result, that is 0.0001.
How is the probability so high?
I'm going to talk about it now in a moment.
Sorry.
Please. Okay, did you write these down? So let's compare the two different situations that we have. So, in the top two situations, the person, what did they get on their test? A positive or negative?
Positive.
They got a positive test result. They got a positive test result. There's a 33% chance they're a drug user and a 67% chance that they're not a drug user. But the situation is actually much better in the negative case. If a person gets a negative test result, what's the chances that they're not a drug user? Nearly 100% chance. If the person has a negative test result, what's the probability that they're actually really a drug user in disguise? Nearly 0. So you can see that getting a negative result and getting a positive result leaves you with two very different situations. In the positive case, we're not very confident that the person is actually a drug user or not a drug user. But if the test result is a negative, we're pretty clear. If it's negative, it's very likely that they don't use drugs and very unlikely that they do actually use drugs. The reason for such a difference between the two situations comes down to the fact that so few people are drug users in the population. If you think about it, what's happening here is so few people use drugs that if you get a positive result, it's actually quite likely that it's a mistake with the test. Whereas if you get a negative result, it's actually quite likely that that's real because so many people don't actually use drugs. So the problem is this. So few people use drugs. That's why the test result is so different in each situation here. If, for example, 10% of people use drugs, then the situation would be quite different. You would feel this number would be much higher. So the point with this question is, at the very beginning it looked like the test was quite good. 99% of drug users test positive, 99% non-drug users test negative. That sounds quite good, but when you actually look at what happens, if the test result is positive, there's only a 33% chance that they're actually a drug user, which is kind of low. Does anybody know what you call this situation where the test result is positive, but they're actually not a drug user?
Unfair.
It is unfair, but there's actually a special name for this. It's called a
Practice.
false positive. They got a positive result, but in fact they're not a drug user. That's a false positive. This situation here, it's a negative result, but they're a drug user. Unlikely, but what is this called? A false negative. They got negative, but they're actually a drug user. Unlikely to happen, but can happen. False positives are much more likely. Someone does not use drugs, but their test result is positive. That's much more likely to happen than false negative. So if you get a positive test result, I won't hold that against you and think that you're a drug user. If you get a negative test result, I believe that's probably more true. Okay. This is why it's important to retest people. Yeah. That was a hard example, but an important example.
What if they get a false negative and then they test them again and then they get a positive? Like how would they know like if they test them
If it happens like that, they'd probably have to do a test a third time. If the first and the second test results match, they'll stop. But if the first and the seconds are different, then they'll probably do a third test.
So it's like they're taking probability. They're still taking probability.
Oh, it's still taking probability, yeah. It's still possible through bad luck,
Yeah.
you're a non-drug user but get a positive test result twice in a row. In fact, that in this story, that will happen 11% of the time.
Like I just told like even the whole system is like understand? If it was
Yep.
then
Yep, exactly. Yes, exactly, this is true. The doctor doesn't think about it as deeply as this. But if it was a court case, then more thought is given to the probabilities. But you're right, in a hospital, it's unlikely the doctor will actually do calculations of how likely it is the person's a drug user. Okay, we'll finish